Concentric eccentric contraction. You're probably tired of hearing that, right? And you're wrapping your brain around what concentric is, what eccentric, and we also have isometric, not depicted here, but you definitely have this lifting phase where you're overcoming gravity, and you have this lowering phase where you're generally going with gravity. But what we're going to talk about now is more of what's happening underneath. When we looked at this muscle architecture of this at the sarcomere with this interaction of these myofilaments, and you have these thick and thin filaments that are sliding over each other. And at the top here, you see muscle in its relaxed state. And then down here, you see muscle in its contracted state. So what we want to talk about is how are we going from here to here in this, from a relaxed position to a concentric contraction, a shortening aspect. And when you look at the muscle architecture, you remember we said the sarcomere is the business end. So you have sarcomere, 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 sarcomere. And this is part of the myofibril. And you have these myofibrils bundled together. And this is the muscle fiber. And you have other structures in here, like you have the cellular nucleus, you have the sarcoplasmic reticulum. And all of these structures are part of this interaction of these myofilaments. And you can see here the thick filaments and the thin filaments. And these are interacting to form cross bridges and ultimately end up in muscle tension generation. So the first thing here is, here's your muscle fiber, and inside that fiber you have the myofibrils, and these are the sarcomeres you can see there, and you can see the protein filaments there, the little red and white dots. But you have the sarcoplasmic reticulum here, and this sarcoplasmic reticulum, this is the repository of calcium, and it is always sucking calcium out of this matrix here, out of the cytosol, so that the calcium is here. What will happen is you have this T-tubule here, and you have this neuromuscular junction, and the motor neuron is coming down and it's connecting to all the muscle fibers, so that's making the motor unit, and it is releasing neurotransmitter, and that neurotransmitter is acetylcholine, and that acetylcholine is going down that's continuing the action potential down the T-tubule, and that action potential forces the sarcoplasmic reticulum to release calcium. And that calcium release, so here's the acetylcholine, that calcium release starts to interact with this actin, myosin, tropomyosin, troponin complex. So these are all the protein filaments that are involved in this sliding filament theory. Now, what wants to happen is you have this, what we need to happen, and we said in different lectures, that muscle tension is dependent upon the quality and the quantity of the cross bridges that are formed. And what a cross bridge is this myosin, this globular head of the myosin, is actually connecting to an active binding site on the actin. So the cross bridge, and ultimately in order for muscle tension to generate, is you need to have a connection between the myosin and the actin. Unfortunately, that actin, or not unfortunately, but that actin's binding site is blocked. And it's blocked by this tropomyosin complex. So this tropomyosin is blocking those binding sites, and what ends up happening is calcium connects to this troponin. And what that troponin calcium does is it forces that tropomyosin to move, and it exposes the binding site for the myosin. So muscle contraction is really generated by the presence or absence of calcium, and that's determined by whether there's a go signal coming from the nervous system or not. And so we have these different, remember we had different muscle length tension. So the mid-range, your body's the strongest because you have this optimal overlap for cross-bridging opportunity. When you get too short, you're running out of cross-bridging room. And when you get too long, you don't have enough overlap there. So there is definitely a movement. You can see that the myosin doesn't move. And what's happening is the actin is coming in from both ends through this shortening. So what you see here is this cross-bridging cycle, and this is the sliding filament theory, and you got these 4 steps that are rotating through. And what you're seeing here is this cross-bridge formation. You're seeing this kind of power stroke thing that's happening where you're getting this pullback, and then you're getting a release and a recocking, and then the process starting over and over again. And as long as calcium is in the matrix and it's exposing the binding site, and there's enough of energy, in this case ATP, this is ATP here, and we'll talk more about this in the bioenergetics unit when we get to that. But as long as ATP is there and calcium is there, you're getting this cross-bridging cycle over and over again. And so the globular heads are, the myosin's reaching out, forming the cross-bridge, and cinching things up and pulling in the opposite direction, and then grabbing again and pulling in the opposite direction, grabbing, and it's shortening up, ratcheting up as it's going through its lengthening, or in this case, shortening component. So I have this image on the Blackboard shell, and I think this is a great schematic. It goes each step. There's the 5-step process. It's the action potential coming down the line, down the neuron. This is the motor neuron. It's hitting the synaptic gap, or the neuromuscular junction in this case. It's releasing acetylcholine, the neurotransmitter. That's continuing the action potential down the T-tubule. It's stimulating the sarcoplasmic reticulum to dump calcium into the matrix. The calcium binds with the troponin, which then forces the tropomyosin to move, exposing the binding site on the actin molecule. And then the cross-bridge can form, and that's the cross-bridge formation. Doesn't necessarily mean muscle contraction, it just means that cross-bridge is formed, and as long as there's ATP, enough energy, cellular energy to do its job, so as long as there's enough gas in the gas tank, it will start to go through that cycle of connect, pull, connect, pull. This is another image. This is the one from your textbook that shows the same thing. I think there's a lot more going on, but again, acetylcholine coming down, continuing that action potential. The red is that current or the signal, and it's going to terminate in muscle tension generation through forcing the sarcoplasmic reticulum to release calcium. That calcium binds to the troponin. The tropomyosin moves, and it forms that cross bridge. So that's the relationship. And as long as calcium is there, you're going to get this cross bridge formation. The natural state is this sarcoplasmic reticulum is constantly trying to suck calcium out of this cytosol, out of this area, and that's the natural byproduct. So once that go signal stops, that acetylcholine is no longer being released. That action potential is no longer reaching here. That calcium is being sucked back in. Once that myosin head lets go to connect again, it has nothing to connect onto. It's blocked, right? You can see the tropomyosin is blocking the binding sites, whereas here, the binding sites are exposed because calcium is in the matrix. So you're getting contraction when calcium is there, relaxation when it's not. This is just showing a more close-up view of this whole process. You're seeing the overlap here between the myosin and actin. You can see the binding sites being blocked, and here your globular heads. And again, going through this process of connecting, pulling, connecting, pulling. And this process is it's not all the globular heads are connecting at the same time. They're rotating through. So one's grabbing on and pulling while one's relaxing and grabbing the next one, and it's cycling back and forth. And then this is where that image that you find on Blackboard of that video of the millipede walking, and the millipede is representing the myosin, and these are the globular heads here. So when we're looking at this, we have the globular heads that are here, and this line that you see here, this is the actin. And you can see that when this millipede is walking, it doesn't have all of its legs on the ground at any given time. So at any given time, you have a few of the legs that are connecting. So these are the cross bridges that are forming. You have some that are pulling back. These are going through the power stroke. You have some that are released that are recocking, and then they're going to reattach again based on the movement. And so you're getting this forward progression, but not all the legs are happening at the same time. So again, if you think of the millipede as the myosin and the globular heads as the legs hitting the ground, that's basically how this is happening. But now pretend this thing has legs 360 degrees all around it, and then you have actin all the way there. That's happening all at the given time. And again, this is only happening if calcium is in the matrix, forcing the tropomyosin to move out of the way so that these legs have something to connect onto. If that binding site is not there, if it's not active, these guys go to connect, and there's nowhere to connect. And then as the other legs start to lift up, the muscle slides right back down into its resting tone. So again, that's the millipede as the myosin head, and that's exactly what it's doing. It's connecting, releasing as it's going through its cycle. So that's it for the muscle contraction process. And I don't know if I would necessarily memorize everything, but I would definitely know the things on this slide right here, and I would definitely know the structures like the sarcoplasmic reticulum. It stores calcium. Understanding this relationship of troponin, tropomyosin, actin, myosin. These are the primary protein filaments. There's other protein filaments that are in here, but these are the major players for the sliding filament theory. But that acetylcholine has to trigger it through that action potential, and it's the presence or absence of calcium for the cross bridge formation, and that in order for contraction to occur, you need to have ATP. So you can't just have cross bridge formation. It has to have calcium, and that's there because of the action potential. And you have to have enough energy, enough fuel. So you just don't need the keys of the car to turn it on. You also need gasoline in the tank to be able to run.